Okay, let's dive into this. Welcome to the Explainer. Today we're basically stepping into the shoes of a biochemical detective. We're going to tackle a classic laboratory mystery, and we'll look at the seriously ingenious method used to solve it, Barfoed's Test. If you've ever wondered how scientists actually decode the unseen, microscopic structures of the molecules we consume literally every single day, well, you are absolutely in the right place. So, picture this. You're standing right there at a typical lab bench. Right in front of you are two test tubes. Both of them contain liquids that are perfectly clear, completely transparent, and, honestly, entirely identical to the naked eye. But chemically? Oh, they're vastly different. One holds a simple sugar, and the other's got a complex one. So the challenge is officially on. How in the world do you distinguish a simple sugar from a complex one when your eyes alone just can't tell the difference?
To solve this, we need a solid game plan. Here's our roadmap for today's explainer. First up, the sugar challenge. Then, we'll hit the chemical principle. After that, we'll walk through the actual lab procedure step by step, and we'll wrap it all up by interpreting the results.
All right, let's jump straight into section 1, the sugar challenge, differentiating carbohydrates.
This is where we meet our main investigative tool. Barfoed's test is a biochemical test that's specifically designed to distinguish between monosaccharides, those simple single-unit sugars, and disaccharides, which are slightly bulkier two-unit sugars. And this isn't just some abstract theory. It's actually a fundamental bread-and-butter procedure performed in undergraduate labs all over the world to identify simple sugars when you're handed an unknown sample.
So how exactly does this thing work? Let's move to section 2, the chemical principle. How the test works.
The magic really starts with a highly specific chemical concoction called Barfoed's reagent. It's a solution of copper acetate mixed into dilute acetic acid. Now listen, that second ingredient, it's incredibly important. The dilute acetic acid creates a strictly acidic environment. And this acidic medium is absolutely crucial. It's the exact condition we need for our chemical clues to eventually show themselves. Without that acidic environment, well, the whole investigation basically falls apart.
Now, what's really interesting about this slide is how this invisible, molecular-level chemistry suddenly turns into a highly visible physical clue. Inside that acidic medium we were just talking about, a reduction reaction happens. The copper-2 acetate from our reagent gets reduced down to copper-1 oxide. But what does that actually mean for us as lab detectives? It means this invisible, dissolved chemical transforms into a stark, highly visible red precipitate, a solid that just drops right out of the liquid. That red solid, that is exactly the fingerprint we're hunting for.
But here's the real secret to telling these two sugars apart. It's all about speed. Think of it like a chemical foot race. On the left side, we have our monosaccharides. Under these highly specific acidic conditions, they act exactly like sprinters. They react rapidly. Boom, done. But on the right, our disaccharides are much more like slow walkers. They react very slowly, or honestly, they might not react at all. The reaction itself is identical, but the pacing is a whole different ballgame.
All right, let's shift into action mode and see this in practice. Section 3, Lab Procedure, Running the Investigation. Every good detective needs their kit, right? Setting up the lab bench requires just a few key pieces of apparatus. You'll need the Barfoed's reagent we just talked about, some clear test tubes so you can actually see the reaction, a pipette for precise measurements, a water bath that can be brought to a boil, and obviously, your mystery sample solution.
Let's walk through the exact methodical progression of the experiment. Step 1. You take exactly 2 milliliters of Barfoed's reagent and put it in your test tube. Step 2. You add 1 milliliter of your sample. Step 3. Give it a gentle mix just to make sure everything's combined nicely. Step 4, and this is where the chemistry really wakes up, you carefully heat that mixture in your boiling water bath. And finally, step 5, you observe. You watch closely for that telltale red precipitate to form.
But wait, I want to pause right here. Notice that number on the screen, 1.5. This represents the midpoint of the absolute most critical metric in this entire test, 1 to 2 minutes. That heating step, it has to happen for precisely 1 to 2 minutes. The time factor is literally the key to unlocking this whole mystery.
Which brings us perfectly to our final stage, Section 4, Interpreting Results, Reading the Clues.
So the crucial point is right here on this matrix. This is exactly how you confidently declare the identity of your mystery sugar. Check out that top row. If you heat the tube and you see a rapid red precipitate form right within that strict 1 to 2 minute window, you've got a positive result for a monosaccharide. Mystery solved, it's a simple sugar.
But looking at the second row, if you pass that 2-minute mark and the reaction is delayed, or hey, if no precipitate forms at all and the liquid just stays clear, that is a massive clue that you're looking at a disaccharide.
But hold on. As a lab detective, you have got to avoid the most common trap out there. Listen closely to this precaution. Do not overheat the solution. Seriously, if you ignore that strict 1 to 2 minute time limit and just let the test tube sit there in the boiling water bath, you'll completely ruin the investigation. Why? Because prolonged heating actually starts to break down the complex sugars, and that means those disaccharides will eventually trigger a reaction, handing you a total false positive. If you lose track of the time, you lose the entire integrity of the test.
Let's bring it all together with this quote straight from the source material. Barfoed's test is a simple and effective method to differentiate monosaccharides from disaccharides based on reaction time. Honestly, that perfectly sums up our entire biochemical investigation. By leveraging an acidic environment, a copper reduction, and a super strict stopwatch, we can turn totally invisible molecular structures into this blazing red signal. We've cracked the case of the simple versus complex sugar today just by understanding one highly specific chemical reaction. But it really makes you think, what other invisible chemical secrets are just waiting to be uncovered in the lab? Thank you so much for joining me for this explainer. Keep questioning, keep observing, and I will catch you next time.